Okay, so we're doing our topic of algae as a source of biofuels. And then for a roadmap,
Um, I'm Mia, and I'm going to be doing the introduction and background.
My name's Ashley, and I'm doing algae cultivation and growth.
I'm Ellie Decker. I'm going to be doing the biofuel extraction and conversion.
My name's Tyler. I'm doing the economical and environmental impacts.
I'm Blake. I'm doing current research and tech advancements.
My name is Emiliano, and I'm doing real world applications of the future outlook.
So good morning. I'll be introducing our topic as algae as a source of biofuel. So what is algae? Algae is a simple photosynthetic organism that uses sunlight, carbon dioxide, and water to create energy and gas. They come in many forms, from tiny microscopic species called microalgae or macroalgae. So, okay, so there's two types of algae. Um, Macroalgae is more commonly seen as like sea kelp or sea lettuce and is most commonly used for biomass and biogas. And then microalgae is a little bit less common and most commonly used for fuel. Um, Algae can be found almost everywhere in oceans, lakes, and ponds, and even in wastewater. They thrive in a variety of environments, including freshwater, saltwater, and even brackish or polluted water. Um, For biofuel production, microalgae are the most useful because they grow quickly and produce large amounts of oil that can be turned into fuel. Um, so why are scientists using algae as a fuel source? Compared to traditional crops like corn or soybeans, algae grow much faster and can produce up to 30 times more oil per acre. They also don't require farmland or fresh water, which means they don't compete with food crops, which makes them a much more promising source. Um, Plus, algae can absorb large amounts of carbon dioxide, helping reduce greenhouse gas emissions. Because of this, algae are considered one of the most promising renewable resources for sustainable fuel production. Um, Overall, algae can offer a clean, renewable, and highly productive source of energy.
Algae is photosynthetic, which means that it requires sunlight and carbon dioxide to grow. And photoautotrophic organisms make their food by using light and converting inorganic materials like carbon dioxide into organic materials. There's also some heterotrophic algae that does not require sunlight to grow, but it's more efficient to harvest photosynthetic algae because sunlight is a free source of energy. The most successful growth of algae happens when temperatures are within 60 to 80 degrees Fahrenheit, and the nutrients that photoautotrophic algae need to grow successfully are light, carbon dioxide, water, salts, and inorganic materials. These elements are used to build the algae's cells, biochemical, and cellular components. And then during large scale production of algae, there needs to be constant mixing so that all algae is receiving the nutrients and sunlight it needs. There are two main ways to efficiently grow algae, and they include using open ponds and enclosed photobioreactors. In open ponds, that's designed like raceway of like a snake paddle. A paddle wheel at one end of the raceway and rotates continuously to mix and circulate the algae. Nutrients are routinely added to the paddle wheel and distributed throughout the current. One downside to this process is that water lost due to evaporation and biomass production is limited to the size of the pond. And a picture of that is on the very top. And then in enclosed photobioreactors, they're most commonly tubular and found outdoors under natural light. Algae biomass is constantly flowing by using a mechanical or airlift pump, and the tubes are usually less than 10 centimeters in diameter to maximize sunlight penetration, and the nutrient broth is pumped through the tubes. And then one downside to enclosed photobioreactors is that oxygen will accumulate inside of the tubes and potentially poison the algae. But to prevent this, the broth can be bubbled with air to remove the excess oxygen. And a picture of that is on the very bottom.
Regarding harvesting, which begins the process of extraction, the microalgae are very small and are found suspended in the water, which makes extraction challenging. Process Processes like centrifugation, filtration, and flocculation are used to harvest from the biomass. This may look like spinning rapidly to separate algae from water, using a mesh net filter to trap the algae, or adding chemical agents to cause clumping, all achieving a separation so the algae can be collected. The algae is then broken down so that the lipids are able to be reached for use. In simpler terms, cell disruption is the part of the process where the algae is open to release the oils or lipids that they store. This is necessary because algae has thick cell walls that protect these oils, and these processes must be performed in order for them to be reached. This can also be done a number of ways, for instance, mechanically, which physically shakes and bursts the cells, or chemically, where substances are used to dissolve and weaken the cell wall. Once lipids are extracted, the last step in the extraction process consists of organic solvents such as hexane or chloroform methanol mixtures being used to perform solvent extraction. These are very effective but costly and energy demanding, while not being environmentally friendly, which raises ethical and sustainability concerns since algae is a natural resource. Because of this, researchers are exploring greener and more efficient extraction methods. This is where the conversion process begins. Oils that were extracted from the algae are converted to biofuel through transesterification, which is a chemical reaction with an alcohol like methanol and a catalyst. This reaction will create a fatty acid methanol esters, which are the chemical compounds in biodiesel, and glycerin is created as a byproduct. There are other ways to get the final product biofuel. Transesterification is not the only way. Things like hydrothermal liquefaction, pyrolysis, and gasification are alternatives that are considered and used because they can process a wet biomass and avoid the drying process steps, which are very cost intensive. These methods are becoming more common as research advances because they can be more environmentally friendly, along with their low cost and overall more efficient compared to traditional transesterification. Depending on which conversion method that was used, macroalgae can make a number of final products, not just biodiesel, which was mainly focused on, but bio-oil, methane, ethanol, and hydrogen are all possible products. These all have the potential to act in the same way as fossil fuels while lowering greenhouse gas emissions, though they have obvious room for improvement in efficiency and cost effectiveness.
As as for the environmental impacts, using algae as a source of biofuels considered to have many pros while only having a few cons. Some of the reasons this consists of how renewable that it can be and how it's able to capture carbon dioxide during photosynthesis. This greatly reduces greenhouse gas emissions, and they have the ability to grow in wastewater and even on non-farmable land, and this minimizes the competition with crops. On the other hand, large-scale making and production can lead to burn through significant amounts of water and nutrients. Doing this to a large scale while not being able to control it to that large scale can cause pollution and habitat disruption. Overall, algae being used as a biofuel offers several benefits towards the environment, but having control and care over the mass production of algae is essential. And then for the economic impacts, while algae biofuels are promising and further research of them being used or being done daily, they're still very costly compared to fossil fuels. And growing and producing algae at a large scale, where it's able to be used everywhere worldwide, is very expensive and requires proper technology. For some pros, they not only create jobs, but they also support rural economy. And as research and technology improves, as for anything in the economy, algae biofuels will become more efficient and cost effective. There's a bright future for algae as one of the mainstream biofuels, but it's important to keep in mind the possible downsides.
All right, current research. The first major focus is genetic engineering. Scientists are using tools like CRISPR and selective breeding to create high oil strains, basically algae that store more lipids, which are going to be the raw materials for the biodiesel. These engineered strains are also designed to grow faster and stay stable in outdoor environments, which helps make large-scale production possible. This connects to the next point, faster growth and better carbon dioxide uptake. Modern algae research doesn't just look at how much oil algae can produce, but also how efficiently it can absorb carbon dioxide. Some new strains actually thrive on industrial carbon dioxide emissions, which means algae could double as both a fuel source and a form of carbon capture. Another big research goal is developing stress-resistant species. These are algae that can handle harsh conditions like high salinity, temperature changes, or intense sunlight. That's important because it means that we can grow algae in non-farmable areas, using seawater or wastewater rather than competing with crops for freshwater or land. Finally, we're seeing real movement in from lab to pilot scale breakthroughs. Projects like those at the National Renewable Energy Lab and in Europe have already scaled up algae cultivation from small test tubes to outdoor tanks and ponds. This is a critical step, and it shows how technology can actually work outside of controlled lab conditions. And then in this picture, it shows how the YNB60 strain from their genetically modified different algae um, had the highest amount of lipid percentage in it. Now, advanced cultivation technology. Now that we have better strains, the next challenge is how to grow them efficiently. And that is where smart photobioreactors come in. These are advanced closed systems equipped with sensors and AI technology. They constantly track light, carbon dioxide levels, pH, and nutrients, and automatically adjust the conditions to keep algae growing at maximum speed. That kind of real-time control allows for continuous harvesting systems, meaning we can collect algae biomass without stopping growth. This makes the entire process much more efficient and less wasteful. Another key innovation is connecting these photobioreactors to factory exhaust pipes or power plant emissions, as seen in this picture. Instead of letting carbon dioxide gas go into the atmosphere, the gas is captured and piped directly into algae tanks. The algae uses it for photosynthesis, effectively recycling industrial carbon dioxide into a clean energy resource. Finally, when the algae are ready, the biomass can be processed using hydrothermal liquefaction or HTL. This is a conversion method that turns wet algae directly into biocrude oil without needing it to dry first. This is a major energy saver and an important step towards large-scale food production. Now, how do we keep this going for a long time? What you see here is a pilot-scale algae cultivation facility, which represents the next step beyond the lab. Instead of focusing only on fuel, these sites operate as biorefineries, producing multiple valuable products at once. They produce biofuel, animal feed, fertilizers, and even specialty chemicals or nutritional supplements. By selling several products, these facilities reduce costs and make algae-based fuel more competitive with petroleum. Around the world, pilot plants are scaling up just like the one shown here. Researchers are testing different designs from open ponds to enclosed bioreactors to find the most efficient systems. And importantly, this progress is paving the path to commercial aviation fuels. Several airlines and research programs have already completed successful flight tests using algae-based jet fuels. These fuels can blend directly with existing aviation fuel, meaning no engine modifications are needed. So the combination of advanced genetic engineering, smart reactors, and multi-product biorefineries is creating a realistic roadmap towards sustainable aviation and carbon neutral energy.
All right, so key challenges to commercial viability. For all its promises, algae biofuel faces a series of significant and technical economic hurdles. The biggest challenge is its cost. The process involves carefully cultivating the algae in open ponds or complex bioreactors to harvesting these tiny little cells from huge volumes of water, and then to finally break them open to extract the oil, which are all incredibly energy intensive and expensive. Basically, it's a fragile system. A single contaminant can wipe out an entire crop. And so the question we must answer is, does the process yield significantly more energy than we put into it? Currently, the energy balance is often negative, and successfully scaling these delicate processes from a controlled lab setting to an industrial size or city size scale is a monumental challenge to the industry we must overcome. Slide. And so some compelling real world advantages. So why go through the trouble? So the reason why is because the advantages of algae are almost too good to ignore. First off, it's incredibly efficient, yielding up to 20 more oil per acre than soybeans. This means we don't need to convert vast areas of farmland from food production to fuel production, completely sidestepping the food versus fuel dilemma. Instead, we can grow it on marginal land and even in deserts using salt water. Furthermore, algae doesn't just avoid harming the environment, it actively helps it. It consumes carbon dioxide, making it a partner for carbon capture. From industrial plants, it can be used to clean nutrients from wastewater. And finally, the fuel itself is superior, particularly for aviation, where it's high energy density and is a perfect match for replacing conventional jet fuel. Slide. And so its future outlook and path to mainstream. The future of algae isn't just about fuel. The industry is undergoing a crucial evolution, moving from fuel only to an integrated biorefinery concept. This is the most promising path because the idea is to use the same batch of algae to produce or to extremely high value products such as omega-3 supplements for health foods, pigments for cosmetics, or proteins for animal feed. And they use the revenue from these products to subsidize the production of lower margin fuel. This makes the entire operation economically viable. Slide. And so what's it going to take to go on mainstream? Well, reaching it to mainstream requires more than technology. It demands a powerful partnership. The government must create a level playing field with policies such as carbon pricing. Private investors must fund the first large-scale biorefineries, and scientists must deliver low-cost breakthroughs to lower costs. Only this alignment can bridge the gap to a sustainable future. Only this alignment can bridge the gap to a sustainable future as well. And here's our reference page. Any questions for any of us?